thank you very much for the introduction, and many thanks to the organizer for the invitation to present the result of my team. So let me start, slide are not, okay. Let me start by acknowledging the people having contributed to this work. My colleagues Maria Amanti and Florent Babou, our PhD students, as well as our former PhD students and postdoc, as well as the theoretician of working in our team, Perola Milman and Nicolas Fabre, who now left for postdoc. Now we also work with clean room engineer, both in our laboratory, Material and Phénomène Quantique, and our collaborator in the Center of Nanostructures and Nanotechnologies in Palaiseau for the growth and the processing of the sample. Now, in these last years, quantum state of light has been used as a powerful resource to reach important achievement in several domains of quantum technologies. And we could mention the record distance in quantum communication with the missile satellite, the work on quantum computational advantage in boson sampling, or quantum simulation of vibrational motion of molecules, or again, the utilization of squeezed state of lights in advanced LIGO interferometer. And in this context, photonic quantum technologies are a promising platform for the development of a large variety of scalable systems for quantum information protocols in real-world applications. And important progress has been done on the three main stages: the generation, the manipulation, and the detection of quantum state of light. So now that promising results have been obtained on many different systems, we are living an exciting phase with many open challenges and perspective to implement and fully exploit the potential of photonic quantum technology. So this ranges from the integration of several functionalities in the same chip to the hybridization of different platform, or from the exploitation of a high-dimensional degree of freedom to testing the performances of these new devices in quantum information protocols. And our team addresses some of these issues working on the aluminium gallium arsenide platform, and my talk will be divided into three parts. The first one, in which I will explain the working principle of our devices, and I describe the basic properties of the generated quantum state. In the second part, I will move to our results about the engineering and manipulation of quantum frequency states. And in the last part, I will present our most recent work on the implementation of a quantum network using one of our aluminium gallium arsenide chip. So first of all, let's recall what are the strong points of this platform. So the high confinement of light in aluminium gallium arsenide leads to small footprint devices. Here you can see a picture at the scanning electron microscope of one of our devices. The scale here is 2 micrometer. Then you can exploit the direct band gap of this platform in order to do electrical injection of the device. We have high electro-optic effects, which allows to implement on-chip fast routing and manipulation of photons. And finally, the on-chip and hybrid integration with superconducting detectors has already been demonstrated, as you can see here in this picture taken from a paper of Peter Michler's group. So the generation of quantum state of light in this platform can be done either by using quantum emitters, and there is a strong community working on quantum dots. So bright quasi-deterministic sources have been demonstrated working at cryogenic temperature. And the alternative is to exploit nonlinear optical effects to generate photon pairs, either by spontaneous parametric down conversion or spontaneous four-wave mixing. And in this case, the source is non-deterministic, but photons are emitted at room temperature and in the telecom band. So we can, and moreover, we can easily play with different degree of freedom of light. So in our team, we exploit the spontaneous parametric down conversion. And in this process, you have to satisfy the condition of energy and momentum conservation. Now, gallium arsenide is isotropic, so in order to satisfy momentum conservation, you have to do attention, and this requires a bit of engineering of the dispersion properties of the device. And in this talk, I will speak about devices based on two different phase matching schemes. So up to now, we have been mainly interested by type 2 phase matching schemes in which the generated photons have orthogonal polarization. In the first phase matching schemes that you can see here, the three interacting modes, pump, signal, and other, are collinear and co-propagating. In the second one, the pump beam impinging from the top of the waveguide, and signal and other mode are counter-propagating. So note that in this case, we have two possible interactions. Either the horizontally polarized photons come out from the right and the vertically polarized one from the left, or vice versa. So the typical pair production rates in this device is comprised between 10 to the 6 and 10 to the 7 pairs per second. One interesting point is that the choice of the phase matching configuration has a strong impact on the tunability curves of the device, as you can see here. So in particular, the signal idle wavelength is tuned by means of the pump wavelength in the co-propagating schemes, while in the counter-propagating scheme, we play with the angle of incidence of the pump beam. And the phase matching scheme has also a strong effect on the joint spectral intensity. In the case of the co-propagating beams, the generated photons are emitted over a large spectral bandwidth and present strong wavelength anti-correlation, whereas in the case of the counter-propagating phase matching scheme, the bandwidth is much narrower, 2 to 3 orders of magnitude, and frequency correlation can be engineered via the pump beam profile, as I will show in the second part of the talk. So before passing to our most recent result, I just summarize here some former achievements obtained with the two types of device. So the co-propagating geometry is particularly suited to exploit the direct band depth of the material. Indeed, the insertion of a quantum well within the device and the doping of the structures to realize a p-n junction has allowed us to demonstrate the generation of photon pairs by electrical injection and working at room temperature. And the same geometry with passive samples has allowed to reach high values of indistinguishability and energy time and polarization entanglement. On the other hand, the counter-propagating scheme led to the first demonstration of polarization entanglement some years ago in a semiconductor waveguide. And more recently, we were able to demonstrate the monolithic integration of a source and a beam splitter that has been used to perform a Hamburg-Brown and Twist experiment to demonstrate a non-chip heralded single photon source with a beam splitter. Okay, let's now come to the second part of my talk, which is devoted to engineering and manipulation of quantum frequency state. Let's say that in these last years, we are witnessing a growing interest towards entanglement into high-dimensional degree of freedom, since that can be used to increase density and security of information coding and processing, and can enhance flexibility in quantum computing. And various demonstrations has been done using different degree of freedom. For example, orbital angular momentum, or spatial mode, and frequency. And among these different approaches, frequency is particularly attractive since it is compatible with the existing telecom network and its capability to convey large-scale quantum information using a single spatial mode. And a particular class of frequency states, namely biphoton frequency combs are attracting a growing interest. Indeed, this state can be generated either by spontaneous parametric down conversion or spontaneous for wave mixing in the presence of a cavity. And their interest come from the fact that they can be seen as qubits, and they have an interesting potential for quantum computing and quantum communication application. So a review about the generation and manipulation of such kinds of state in microresonator based on spontaneous four-wave mixing can be found in this paper here, appeared in Nature Photonics. Now, if you look to our devices, it is easy to see that they naturally are nonlinear cavities. Indeed, the refractive index contrast between the semiconductor waveguide, which can be seen here, and air at the facets level creates a Fabry-Perot cavity surrounding the nonlinear medium. So the joint spectral intensity of the emitted quantum states presents a frequency comb structure with a typical bandwidth of around 9 terahertz and the free spectral range around 20 gigahertz, giving a number of peaks in the bandwidths of around 500. So in a recent work, we have proposed a method to generate and control the symmetry of such biphoton frequency comb, and we demonstrated using one of our chips. The method can be applied, of course, to any system generating photon pairs with the Chi2 medium and the cavity, followed by a polarizing beam splitter and a delay line. So you can see the main ingredients of these: the crystal, the cavity, the polarizing beam splitter, and the delay line. So the quantum states at the chip outputs can be written in the usual way as the integral of the signal idle frequency of the joint spectral amplitude times the cats representing the signal idle state. It is convenient to rewrite this expression using omega plus, omega minus, which represents actually the direction of the energy and momentum conservation relation. So the GSA in this expression consists of 3 terms. A term which is related to the pump spectrum, a term which is related to the phase matching condition, and then a third term related to the cavity effect, which will depend on the transmission of the signal and the either photon at the facets. So by considering a broadband pump beam and the cavity having a free reflectivity of 80%, we can simulate the result joint spectral intensity, which presents the patterns of peaks due to this Fabry-Perot effect, as you can observe here. Now, if we choose instead a monochromatic pump beam at the frequency corresponding, for example, to even multiple of the free spectral range, we selectively obtain what we have called a resonant state. Resonant because the intensity peak are present at frequency degeneracy. While if we choose a pump beam at frequency corresponding to an odd multiple of the free spectral range, we obtain an anti-resonant state, like shown here. So let's now see how we can play with the delay line after the deterministic separation of the photon with the polarizing beam splitter to manipulate the symmetry of the state. So the delay line function is composed of 2 terms, one symmetric in omega minus, the cosinus term, and one which is antisymmetric in omega minus. And by choosing appropriate values of the introduced delay, tau, we see that the resonant state can be transformed into a state having a symmetric joint spectral amplitude, whereas an anti-resonant state can be transformed into a state having an antisymmetric joint spectral amplitude. And this is clear by looking at the transformation of the joint spectral amplitude after application of the temporal delay for these two cases, resonance state for tau equal 0 and tau equal to the rounded trip time divided by 2. And you see here we have a symmetric joint spectral amplitude, whereas here in the case of an anti-resonance state, we end up with an anti-symmetric joint spectral amplitude. Now we have demonstrated this method by using a device based on this co-propagating phase matching scheme. And here you can see the experimental reconstruction of the joint spectral intensity and the selective generation of either resonant or anti-resonant state by controlling the pump beam frequency. And the demonstration of the symmetry manipulation has been done by using a Hongu-Mandel setup. Indeed, a Hongu-Mandel setup will read the spatial and consequently the spectral wave function symmetry. And a biphoton state with the symmetric spectral wave function will lead to a bunching on the two photons, whereas one with an anti-symmetric function will lead to an anti-bunching. When no temporal delay is introduced, we know that we are always a symmetric spectral wave function, so a Hongu-Mandel dip is expected and measured. So you can see here what we measure, and the width of this Hongu-Mandel dip is a confirmation that actually we have a very large bandwidth in our state. Then for appropriate value of the temporal delay, we observe either a dip for a symmetric JSA or a peak for an anti-symmetric JSA. This demonstrates the ability to control the symmetry of the generated biphoton frequency comb. If I can comment that the visibility in our case is not high because we have taken the full bandwidth of the biphoton frequency comb. So and then we also relied on the natural reflectivity of the facets. However, this can be increased by applying a high reflectivity coating and filtering a bit the state. And of course, as I already said, the method can be also applied to other systems. For example, system consists of a crystal plus a cavity. This should immediately lead to very high level of visibility. Let's now go to another way to engineer frequency correlation by using the counter-propagating phase matching scheme. As I already said, in this case, the pump beam is transverse with respect to the waveguide, and the JSA of the generated quantum state can be controlled by playing with the temporal and spatial profile of the pump beam. You can see in this animation how the frequency correlation changed, for example, by changing the waist size of the pump beam. So we have implemented a control on the pump beam size in our experimental setup, and you can see here the results of our measurements compared to the numerical simulation. So the agreement is very good, and we prove that we are really capable of passing from an anti-correlated state to a correlated one, passing through a non-correlated state. Note that in this case, the joint spectral amplitude stay always symmetric with respect to particle exchange. And this different kind of correlation can be used to target different kind of application, as for example, pointed out in the reference that I've put here. But we can push further the control on the state by playing also with the phase of the pump beam. And for this, we have used a spatial light modulator. By applying a phase shift on 1/2 of the Gaussian profile, we observe that the joint spectral intensity is modified and display two lobes. So the interesting aspect is that for a pi phase shift, we expect to have an anti-symmetric joint spectral amplitude. But this information cannot be read by looking just at the joint spectral intensity. We need a setup which is sensitive to the phase. So we resorted again to the Hongu-Mandel interferometer, and we indeed have demonstrated either a bosonic or a fermionic behavior with the high visibility and in very good agreement with our numerical simulations. So please note that the originality of this work resides on the fact that we have a complete control on the generated frequency state at the generation state, which without filtering or without doing a post-treatment after the chip. And this is done in a completely reconfigurable manner. So we have recently pushed further this concept by engineering phase matching function, which would lead to an anionic behavior of our two photon state on a beam splitter. So anions presents exchange statistics that are intermediate between bosons and fermions, and they are elementary excitation in quantum in fractional quantum Hall effect and various spin lattice model, and the promising application in topological quantum computing. So we have identified the pump beam spatial profile that would lead to an anionic behavior for the case alpha equal to 1/2, and then tested if we obtained the expected results when sending this biphoton state into a beam splitter. And here you can see the results. Once again, the experimental data are in very good agreement with the theoretical simulation, opening the way to possible application to study exchange statistics effect in simulation problems, or to implement computational or communication protocols using this anionic behavior. So these results are published maybe two weeks ago. So I come now to the third part of my talk, which is devoted to implementation of quantum communication networks. So quantum communication networks enable application ranging from secure communications to blind quantum computing or to distributed sensing. And in particular, the utilization of entanglement allows to deploy trusted node free network, which is an important issue to guarantee the security of the communication. And in this context, a topology that has naturally attracted much attention exploits the presence of polarization and time energy photonic entanglement to distribute polarization entanglement photon from a single source to multiple users that hold energy matched channel pairs. So this concept has been demonstrated and pushed by the group of Professor Ursin, who has proposed a topology allowing to share correlation with every other user in the network, which is a so-called fully connected network. Several challenges came, however, with such an architecture. First, the number of required frequency channels will increase quadratically with the number of users in the network, making the bandwidth of the source a very important feature. And second, the scalability can be of the full architecture can be hindered by the use of cascaded passive elements such as dense wavelength division multiplexer and beam splitter, which will impose a fixed configuration of the network and which introduce high optical losses. So in this respect, the use of advanced multiplexing techniques based on wavelength selective shift offer a number of attractive features for flexible entanglement distribution, as it has been pointed out by the group of Professor Weiner and Professor Lukens. So in our work, we combine our on-chip broadband entangled photon source with industry-grade wavelength selective switch techniques to demonstrate reconfigurable entanglement distribution between up to 8 users. So you can see here the general scheme of the setup. You have here the source. Here you have the multiplexing stage. And then here you have, let's say, the distribution of the photons between the different users and the polarization analysis stage. Here we have used superconducting nanowire single photon detectors. So for this, we have used a device which is based on the co-propagating phase matching scheme, which presents the advantage of emitting photon pairs on a large bandwidth, as you had seen before, displaying strong frequency anticorrelation. Moreover, since we are exploiting a type 2 process of the photons, the photon pairs are also entangled in polarization. And a strong point of the device is that the group velocity difference between the two polarizations within the chip is so small that we need no off-chip compensation. So the photons are directly polarization entangled at the output chip and can be directly sent within optical fibers. So first, we have estimated a lower bound of the fidelity to the psi plus belt states. And we have observed an entanglement bandwidth of 26 nanometer, displaying a fidelity above 95%, and the 60 nanometer bandwidth displaying fidelity above 85%. So this is already a good feature of our source to be exploited in such kind of network. Then we have exploited this broadband polarization entanglement to implement a quantum key distribution protocol with distributing secret keys to multiple user pairs, and we have assessed the long distance performances of this architecture. We observe that the fidelity of entanglement stays above 95% over a distance of 200 kilometers in symmetric links and over a distance of 180 kilometers in asymmetric links. And in both cases, the key rate stays positive for distance above 200 kilometers, which is a very good point for the implementation, for example, of a deployed metropolitan infrastructure. And in the measurement reported here, we have considered just 2 users sharing 2 particular channels, but we have also demonstrated that we can have up to 36 user pairs simultaneously if we use 100 gigahertz channels. So building on these results and exploiting the possibility offered by the wavelength selective shift, we have also implemented a fully connected quantum web networks where each of the n users shares an entangled state with the remaining n-1 users. So as you can see in this graph, the number of 2 users link that we need to connect everybody is n times n-1 divided by 2. And both the multiplexing and multiplexing operation can be done by the wavelength selective shift in a completely reconfigurable manner. So here you can see the obtained results for the coincidence measurement for each 2 users link for network having 4, 5, and 8 users respectively. And as a consequence of the breadband character, we observe a great stability of the signal across the links, leading to a well-balanced network. Finally, we exploit the flexibility of this scheme to demonstrate a quantum network where the signal of each link is optimized following a structural constraint. For example, we can imagine that one of the users can be at the largest distance of the source with respect to the others, and we can then proceed to a bandwidth reallocation in order to balance the entangled photon pair flux in all the links as shown here. So you can see here in red the points that correspond to measurement done before the reallocation of the bandwidth, and then after reallocation we have a stable signal and a balanced signal for all the users. All this work about the implementation of quantum networks has been done in the framework of a collaboration with the team of Eleni Diamanti, who will give a talk tomorrow in the afternoon about secure quantum network, and with Fabian Boitier from Nokia Bell Labs for the conception and the utilization of these industry-grade components. So now I come to my conclusion. I've shown that aluminium gallium arsenide photonic devices present several assets. They work at room temperature, at telecom wavelengths, and are compliant with electrical injection, and are able to generate high quality quantum state. In the future, it will be interesting to increase the on-chip functionality of the devices by implementing, for example, polarizing beam splitters. And actually, we have a very recent result obtained before the summer about this, or by exploiting the electro-optic effects. And another interesting direction is the realization of hybrid device by integrating our 3-5 devices with silicon chip, in which, let's say, photonics components are well developed. So we put together, let's say, the best of the two worlds, and we are working in this direction with ST Microelectronics and with our colleagues at C2N. I've also shown a different way of engineering and manipulated high-dimensional quantum frequency states, open interesting perfecting for a large variety of applications. In particular, I attract your attention on the talk, which will be given by Perola Milman at the conference, related to how we can see and read the state with generate in terms of continuous variable, in particular JKP states, and how we can use this state in the framework, for example, of continuous variable error correction codes. So, but Perola will give a talk completely devoted to this. And we have also other starting projects, for example, the implementation of Waveguide arrays to produce spatial entanglement, the realization of a photon-ion interface with our colleagues working on ion chip. And we are also involved in the deployment of a metropolitan quantum network in Paris, in particular with the team of Eleni Diamanti, who is leading a collaborative project in the region of Paris and devoted to this. With this, I thank you very much for your attention, and I'm ready to answer your question. Thank you very much.
Thank you very much for this excellent talk. And now we have time for questions. Maybe I will ask a question.
Yes.
You mentioned that you have the possibility to induce bosonic or fermionic statistics of the photons. Is there any influence of, because I guess that sometimes it's not only 2 photons that are generated, but sometimes maybe higher number of photons. So for example, 3 or 4 photons at the same time. So do they still follow the statistics?
Yeah,
in particular fermionic statistics?
It's a good question. Actually, I don't have the answer. I think that it should be studied, the case in which we generate more than a photon pairs. Let's say that what we do is that we just choose a pump intensity in which several the emission of several photon pairs is negligible. So actually in the results that we observe, what we measure is the visibility of our Ongu-Mandel state, and we compare the visibility that we obtained with what we should obtain in theory, for example, in this case. Actually, you see that the visibility is not 100%, but the difference between 100% and what we obtained, 88% or 77%, cannot be related to multi-pairs emission up to us, because we have integrated in the simulation the effect of imperfect pumping profile, or the fact that we can pump with not exactly with the good pumping angle, and effects, let's say, related to the experimental setup and to the shaping of the pump beam. And actually this lack of visibility is well explained by this, let's say, imperfect experimental setup. So I think that the effects you mentioned are too small to be visible in our experiment for the moment.
Okay, thank you very much for the answer. There's another question.
Yes, very, very impressive, really, especially the going from the positive to the negative correlated frequency states. That's, you make it look easy, but anyway, my question was about the possibility of maybe going beyond the 2-photon situation, like if you can create these kinds of states for like 3 or 4, or I mean, it seems that your architecture, it would be not maybe too difficult to make subsequent like cascade these systems in order to increase the entanglement between photons. I don't know. Maybe it's science fiction. I mean.
I don't know. What I see in general, people working exploiting spontaneous parametric nonlinear optical effect. There is a beautiful review papers by Alan McDowell and Christine Silberhorn on how to increase the number of photons using a nonlinear chip, using let's say either spatial or temporal multiplexing. And so you can find the interesting information there. So one way would be to put, instead of putting just one waveguide, to put several waveguides on the same chip, and then exploit the fact that we can generate at the same time pairs in these different waveguides. Actually, this is something that has already been done in silicon chip, in which they pump it in two, there were resonator, and so they generated photon pairs in the two, and then doing a Ongu-Mandel between two the photons coming from two different sources. So there is the possibility to go in this direction. We haven't explored the possibility to pump stronger and to go to higher, to generate more than photon pairs in our chip. We were more focused in understanding well and describing well the generated quantum states and the impact of the device on the AlGaAs or the pumping scheme on possible imperfection of the generated state. But of course, it would be interesting to go further and try to see if we can generate state with a higher number of photons.
Great, thank you very much.
There is actually a question from an online question on the chat from Michał Karpiński.
Okay.
Michał, can you?
Yes.
Entangled state into frequency polarization state with the tools that you need to project the state and so on. So it's an interesting direction. The fact that we are using a small structure makes that we have this distance of 20 gigahertz, which allows you actually to control. If you use a bulk crystal, which is longer, then you have a smaller free spectral range, and you cannot achieve the control of each of the.
You don't have the resolution.
Okay, so you use packets of teeth, and so you do slice in your spectrum. So it would be an interesting direction to explore if we are able to control these. So I don't know if I answered your question.
Well, yes, I believe, and even more. Thank you.
Okay, thank you.